I'd love to talk a bit about testing in a software environment and how that can be applied to a classroom environment. So we'll go through a couple of things. I've got a couple of workshops we'll do to get you engaged in both kind of the idea of testing as well as we'll actually do some real TDD, hopefully at the end of the day here. But first, let me get our presentation going, and I'll do a quick introduction. So, all right. So my name's Tanner Welsh. I work for a company called Learners Guild. We are a 10-month apprenticeship program for aspiring software engineers. For the last 5 years, I've worked in adult education, mostly at a company called Dev Bootcamp, which was a 9-week intensive bootcamp for software engineers, doing both instruction as well as curriculum design and software engineering. So I've kind of combined all these three things in my life for the last few years. And one of the things that I've used a lot in my teaching is, well, actually, I teach testing as part of the software curriculum. And kind of learning about how testing works in software, I found a lot of applications for it in a classroom environment. So I wanted to share some of those with you today and hopefully spark some ideas for future creativity in your own environments. So first of all, let me just get a quick sense of the room after knowing where you all come from. How many of you have used testing and software before, like in your own software development or your own software practice? Okay, a few folks have done tests. How many of you have used testing as a part of an assignment or a classroom project? I'm talking about software testing. Okay, all right, so about a third of the room or so. So we'll talk a bit about kind of what a test is, and a software test, of course, I'm saying is something that tests your code and not the student's understanding of the code. So a very big distinction there. This is not a test in the sense of an assessment, but a test in the sense of making sure that the code is working the way that we want it to. All right. Yes, so testing is just a part of the software development practice. It's been around since the beginning of software development. In sort of classical terms, most people in the early days would test after they wrote their software. So there's this big distinction between you're kind of writing software to do a thing, and then in order to make sure that it doesn't crash or have too many bugs, you write some other software to test against it. And in sort of typical environments, these are two separate teams. Oftentimes it's done after the fact. And they're often kind of at odds with each other. There's like usually the development team and then a testing team. And I think in sometime in the late 80s, early 90s, some new theories got developed around a different way to approach testing. And they came up with this theory called test-driven development, or TDD for short. It's not like neuroses or a drug, it's just TDD. And its principle is that you actually write your tests before you write any of the source code whatsoever. You lead by designing the actual behavior of your code, and then, of course, it starts by everything is failing because you have no code, and you slowly work your way towards making each of the tests pass. And one of the main inspirations for it was to kind of keep the constraints of software very clearly defined, and to avoid the meandering that often happens. I'm sure you've probably seen this in your classrooms if you've had students, teachers, that you give them an assignment and they find something really interesting and they build features that like go off for days in a direction, but it's not actually solving the core use case. And so testing helps to kind of constrain your development to make sure that you don't kind of like fall into rabbit holes or build too much or too little in any one direction. And I think it has some interesting implications for how we can use it in the classroom. So yeah, testing for code is just ensuring your code works the way it's supposed to work. And it's about making specifications. So this is the higher level concept of testing, is specifications, which are just how we define the design of a thing. So a specification for something like a basketball, which is inanimate, usually just comes into the properties of that thing. So how big is it? How much does it weigh? What's the material? Those kinds of things. If you have specifications for a basketball and you hand it to a factory or somebody who could produce it, they could theoretically produce the basketball itself. So it's the idea that kind of underlies the design of the thing. When you get into things that have actual movement or behavior like a machine or a ukulele, you can talk about the behaviors of a thing. Well, it has 4 strings. When you pluck one, it plays a G chord. The next one plays an A chord. You can twist it to tune it, things like that. And in the same way that you could have specifications for real-world objects, software is also a system, and so you often begin thinking about software in terms of specifications. So that's the general concept we're kind of working with here. And I'd like to start by a quick example of how we design a bicycle if we didn't have bicycles in the world. Like if you didn't already know or like own a bicycle and you wanted to build one, what are some of the specifications that you would use to define it? Any ideas? Yeah.
It needs to be human-powered.
Human-powered. Okay. So no other motor driving. Yeah.
What's the purpose of it?
What's the purpose? Okay. Yeah. So assuming that our purpose is to create a machine for transporting humans from point A to point B with human power. So there's two purposes there. Yeah, in the back.
It should have 2 wheels.
2 wheels. Okay. 2 wheels, human-powered, with a purpose for movement. Yes.
It is powered by your feet controls the movement and your hands control the direction.
Okay. Feet controls the movement, hands control the direction. Okay.
We need somewhere to sit.
Somewhere to sit. Okay, excellent. Well, these are all roughly the same things that I think I come up with. We have this idea for a bicycle, comes up with specifications. So is this text big enough people in the back to see? Just barely? Okay. So we've got some attributes up at the top, 2 wheels, handlebars, a seat for sitting, pedals connected to a drive chain, that it moves forward at pedaling. So here's some behavior now, that it stops with a handbrake, responds to this action by stopping, and that the front wheel turns when you turn the handlebars. There's some kind of responsiveness in it. So this seems kind of well enough to define what we might think of as a bicycle. And this is where you would start. And this is, if you were thinking about this as a software term, this could become the basis for what's called a testing suite. So in TDD, you would take these ideas and translate them into a suite of tests that you would then use to kind of drive your development of the process, in this case, a bicycle. One of the nice things about this process, too, is that the specifications can be as detailed or as abstract as you want to allow for a lot of variety of implementation. So these same specifications can lead to lots of different implementations. So like all of these 3 different ideas are ways to implement the specifications. You have a bike that has shoes for wheels, doesn't even have to like be the same shape we think of as a bicycle, but they all meet the same constraints. They all solve the same problem that we're looking to solve, but kind of drawing on the creativity of different people's ideas of how they can go about that. Does that make sense? Okay, awesome. That's kind of the key gold nugget in here that I think is that specs can really help you create interesting behaviors, interesting constraints for the design that allow for lots of creativity to kind of blossom inside of that. That have this kind of clear rubric. Okay, so if you're not already sitting at a table with people, please join up with the table, because I'd like to do a quick exercise before we get going into the software part of this. And if you have pen and paper, you can use that. If not, if somebody could take notes, that would be great. So with your table, I'd like you to think of a common machine, a simple one like a bicycle or a ukulele that's also a form of machine. And then write a set of specifications for it. And after you come up with it, you can write all those down, and we'll share the specifications, but not the actual machine. And we'll try and guess what you're actually thinking of. So do as best you can to come up with that list of specifications. Okay, so now what we'll do is for each group to share your list, and please don't tell us what the machine is, and we'll try and see if we can guess what it might be. And so to go first, sir?
So we were struggling with how to make this not obvious. It's like we have a few pieces here. So store liquid at set temperature, hold substance, deliver liquid to substance, filter mixture, deposit mixture and contain.
Any ideas?
Like a coffee machine?
Nice. Coffee machine. Okay, first guess. 2 arbitrary points for this team. Okay. Excellent, thank you. Do you want to go next?
Oh, tell hours?
Yeah.
Sure. I'll read the non-obvious stuff first. 3 wheels. 2 in front, 1 in back. Human powered.
There's a platform to stand on. There's a handlebar and steering column. I think I've given it away now. Yeah. Yeah. That's not everything we have. We haven't had that anymore.
Okay, like one of the ones where you just like, the pedal scooter. Okay. Excellent. 5 points for everybody. Okay, just table over here.
Water has to flow through it, and It has an on and off function.
So the kitchen is over there, if you all would like some more coffee. Okay, all right. A repeat, okay. Unless it was a tea maker, I don't know if you're going for something else there. You could, maybe different cultures would have a different interpretation of that. But. Okay, excellent. And what did y'all come up with?
Okay, for ours, you must be able to control the temperature, and there must be a door to put things in and out of it, to put things in and take them out. And there should be shelves for the item to sit on, and it must have a heat source, and there must be a way to view the items while they're being processed. And optionally, it can have a light to indicate whether or not it's on.
Ooh, an optional spec, okay.
Good, yeah, nice. It was an oven.
I didn't hear what she said. It was a
Oven.
yeah.
Okay, yeah, I noticed that the first 2/3 of those, it could have been a refrigerator as well. And then it's just like the last ones, yeah. Maybe a fridge/oven, that'd be very inefficient, but it could work. Yeah, okay, and last group over here.
We were a little loose with our definition of machine, but here goes. Generally, you start it with your hands. You move your body to operate it. You must move it with your hips rhythmically. It's powered by circular momentum. A human should be able to fit inside of it. Generally, size is 2/3 to 1/2 of the height of a human. It should be round, and it must suggest fun.
Excellent. I'm trying to think if there's like anything else that could possibly fit those descriptions. I'm gonna have to think on that one a bit longer. Okay, thank you all for getting into that. Excellent machines. Thank you very much. So yeah, the point of that really was just to have some fun with the idea of specifications and to show that with that kind of solidified, you can now, like your minds are free to basically think of all the different ways you could meet those constraints with the room that's left open to you. So a hula hoop could be rainbow colored, it could have things inside of it. It's like all these different ways you could implement that concept that still constrains so that the existential constraints. And you have a very clear marker for how well you're doing on your progress towards that. So if you're making an oven, and I kind of ignore the last two, and I build a refrigerator, and then I get the last two, and I realize, oh, actually, wait, no, it's supposed to be hot. Then I know that I've kind of been working correctly for a certain amount of time, and then I've seen my failure happen. So I can correct my progress over time. So let's move now into the context of programming and how we can use testing in a program. So what I'll do to start this off is to give us an example exercise of just defining a function that does some similar operation. So for this case, we're talking about a function that pluralizes a string. And I'll use JavaScript here just because it seems like there's a fair amount of JavaScript in the room, and I can do it online. So beginning with the principles of TDD is I should think about the specifications for this function before I even begin writing any tests. So kind of before I even get to writing any code, thinking about what the purpose of this function is. So its purpose and some of its attributes or behaviors in this case. So in this case, I'm thinking of, well, it should be able to take in words that are singular and make them plural. That's kind of the general purpose. Here's a couple behavioral elements. So it adds an S to words ending in anything but an S, and an ES to words ending in an S. Of course, there's some edge cases here that we can consider in the future, but English is a difficult language to test. And then the last one, this could be like an optional thing, is about like, what about a Latin word that ends in US, like alumnus? Should we change it to alumni? Or if it's alumna, alumni? These are some optional things we could write tests for if we wanted to make sure our function constrained to those boundaries. So this is the English language version. And then the most basic way to do TDD is really just to write conditionals that test for these cases, and to give you some way of getting feedback on whether or not those conditionals are true or false. That's kind of the most elemental test. So I'm going to pop this open in CodePen here. Oh, here we are. So this is a set. I've got a test function that does, can everybody see this code? Is it better if I make it on a light background? Or is that okay? That's good. See? Okay, excellent. So I've got 5 tests for this function. One is that it should be defined, so it can't not exist. It has to exist first. And then I check to see if the outcome of the function, the return value of the function, is equal to this thing on the right. So is pluralizing apple equal to apples? Is pluralizing banana equal to bananas? I try something with rhinoceros, rhinoceroses, and then one Latin word at the end there. And all this is doing right now is just logging true or false to the console. It's giving me this really, really basic, rudimentary feedback about whether or not my code is performing the way that I expect it to. So I actually haven't done any thinking at all so far on what the algorithm should do. All I'm doing is thinking about the end result. And I can start by actually running it. So, oh wait, no, I want my console open. OK, test, run. OK, well, the first thing is I'm actually not getting a failed test, I'm getting an error. And this is kind of the main thing that I find a lot of learners get tripped up on early on in using test-driven development, is differentiating between a failed test and an error in your code. That's a very key differentiator and one that's really useful to get clear on early on, but it actually provides a lot of freedom once you get it. So an error in your code is your code is not running at all. It's failing to compile. If you're using a compiled language in JavaScript, it's failed to interpret because there's some syntax error. A failed test is that your code is working, but it's not working as you designed it to work. So differentiating between those two things, a failure of design and a failure of implementation, is a really important distinction to make. And in testing, you're going to kind of bounce back and forth between these a lot, because you'll try something, it'll make the code break, then it'll make your test break, and you have to fix both of them. So to start off, I need to define this function. And function. That's enough to make my first test pass. That's all I need to do right now is focused on just solving that next thing. So I'll run it again. And what that did is I got 1 true and 4 falses. Now, this is kind of a funky test because I can't actually see which tests are passing and failing. I have to go back and correlate the first one to which true and which false it is. But it's giving me some feedback here. If I wanted to solve the next one, pluralize apple equals apples, I could say, all right, well, it takes an argument that is a string, and I'm going to return string plus s. That should hopefully solve the next test. And it did. Now I've got 3 trues and 2 falses. Because I've got this one is passing, the next one is passing. So this is the basic loop of TDD, is you write some tests, you solve one, make it pass, go back to the next one, solve the next one, just iteratively work your way through. But again, this interface is kind of rudimentary. So like I said, this is the most elemental way to do testing, and it's a really easy way to have, if you have students who aren't familiar with a testing framework, to get involved. To just say, make sure that you write some tests that to either log out a true or false. If you want to get a bit more advanced, you could say log out a message as well, so you can see like what the test was and then whether it was passing or failing. Another really useful thing is to actually be able to see the output. So I want to say like console.log pluralize banana. If my test is failing, I want to see what the output is, so I could run it again. And I should see bananas there. So a better test will give you more of this information. And so in the coding world, there's actually been this proliferation of different testing frameworks. So most languages nowadays actually have built in their standard library a testing framework. So in Python, I believe it's Minitest, or in Ruby, sorry, it's Minitest. There's another one in Python. In JavaScript, there's actually no built-in testing framework, but there are lots of additional libraries you can include. And one of the more popular ones is this one called Jasmine. So I'm going to show you this exact same suite of tests, but written using a testing library that does a lot of the kind of conventional defaults a lot more nicely for us. So same suite of tests, except it's written, the code is a bit more complex. There's a bit more of a library here. And it's meant to be written to be a bit more similar to how we would describe this in our English language specifications. So reading this testing suite, this is an example of a testing suite, I can say that it's describing a pluralized function. It's saying that it's defined, and then inside of my test, it says, expect this function name to be defined. I have a message here. It pluralizes simple words by adding an S. Then I say expect the outcome of these functions to equal these strings, and so on and so forth. So there's a bit more of a base syntax to learn. There's a cost in learning the syntax of a testing framework, but the output is a lot nicer. So with this testing framework, it actually comes with a full GUI showing me different things about my tests. So right now, since I have nothing written, it's telling me that I've got 4 specs. They call test specs here. They're usually interchangeable in a lot of languages. And they're all failing. I'll start with the first one. It's telling me pluralize is defined, and it's giving me this error here. So it actually shows the error message, and where it came from. The next test is also, they're all error messages because nothing is defined. And as I start actually solving this code, the tests will run again, and now I've got one passing. I can see the list of specs here. It shows me, it indents it nicely, so I can see pluralize is defined, that's green, and then the ones that are red are still failing. And as I go through, I get this nice feedback loop of solving additional tests, makes more things go green. Now the second one's passing, and if I want to see some details about a particular test that's working, I can actually see what happened. So in this case, if I thought that this code would solve the third test, it says pluralize adds an ES to words and an S. It'll tell me what my actual result was with my expected result, the difference there. So it's telling me that expected rhinoceros to equal rhinoceroses, and that gives me very clear feedback on how I need to alter my program to meet that specification. Now, of course, making one work doesn't necessarily mean that the previous ones are going to work. So now I've made a previous test fail by making the next test pass. So there's kind of this constant back and forth of, okay, I'm like tweaking my code. And one of the pitfalls of test-driven development, and one that takes a bit of time to get used to, is that can encourage this kind of almost brainless solving of tests. Like, in some ways, you actually want your tests to guide development so well that it's actually you don't have to do much thinking about the resolution until you get to the very end. Because really what I want to do is just solve the tests, make them pass, and the test should be the final determiner. So if I could say, and I guess the dumbest way to solve this problem would be to say if string is equal to apple, return apples. I could keep going with this just for all the test cases. That would be the dumbest way to solve this code, right? Dumb in the sense that I'm not actually thinking about what this code should be doing algorithmically. I'm just thinking about how do I pass the tests. So that's one of the kind of pitfalls of this approach, is that you can get sucked into the cycle of, well, just make the test pass, don't think about the implementation. And the way to get around that is just to make sure that your testing suite triangulates well enough. So it becomes very difficult to just do the brute force approaches, and you actually have to spend time thinking about implementation. Does that make sense? The kind of the differentiation between those two things? Okay. So I could keep going through all these, and we could solve each of the tests, but I'd rather get you all coding and working on some of these yourselves. So this function here, let's see, this is the next two. All right. So let's do some coding before we jump into actually doing some TDD on your own. I'll actually have these in the same groups, or you can switch tables if you want to mix things up. Let's talk briefly about just the TDD theory and how this applies to software. So test-driven development, as I mentioned in the beginning, it's a methodology for programming in contrast to more classical ways where you test after or you don't test at all, and it lets the test guide the development. And it's usually defined by this cycle called red-green refactor. It's a 3-stage cycle that in TDD you're supposed to just kind of do over and over again. So you start with a test, you make it go red, you make it fail, then you make it pass. And then this third stage is one it's kind of optional in a software setting. You really want to emphasize it. In a classroom setting, it might not be as important. But it's to refactor, to say, well, once you've just solved the test, that's not quite enough. That doesn't mean that your code is readable, doesn't mean that it's efficient. All those things don't really go into making the test pass. You're just kind of getting it to pass. And so this third stage ensures quality assurance, basically, in the TDD cycle. And once you have that one done, you can write the next test, make it red, make it green, and refactor.
Is that
Does that third stage also, it seems like inherent in it is addressing the, like, with writing to the text that you talked about before? Like if you're really refactoring, you're not going to accept the Apple's solution because that's not a really good way to test that.
Yeah, that's one thing. I think I probably pushed that a bit to the extreme of like, not many programmers will just like solve a pluralized function by exactly writing to the tests. But what it should do is make you, it's just a time to pause and reflect and make sure that the function is as concise as it needs to be. Yeah, you don't have these kind of edge cases. It's also a time in like kind of more advanced TDD when you'd consider the testing suite and think about what other implications does this code have that we're not testing for. So for example, in pluralize, there's plenty of English language words that might not work with the like always add an S or an ES to them. And so during refactoring, I should be thinking about, well, what's missing from the testing suite that I might want to make sure I add a test for. If you realize that you could find a shortcut in here, that's probably a shortcut that you should be covering with a test. Yeah,
Did you put is the exception, you just talked about it, the exception is built in there? For like anything else you don't collect all exceptions, or is it built in there?
The exception, I'm sorry?
You kind of mentioned it about exceptions to your suite
Mm-hmm.
that you can test for, things that you just don't know. So do you build that in there, or that's outside of it? Do you understand what I'm asking? You mentioned it just now in a way.
Yeah, I think if I understand your question correctly, that you would place those in between these two stages. So
okay.
You don't always start with just like one set of tests, and then you just solve those, and that's enough. Usually test-driven development, you start with a few tests, and as you're developing and solving those tests, you start noticing areas where you should write more. And so that both the testing suite grows and your coding suite grows at the same time. The difference being that you're always writing a test before you write code. So a very common desire that you have as a programmer is you notice something that's wrong with your code or something can be improved, and you just go to fix it right there without adequately thinking about its implications for the larger system. And a test is something that should be testing the implications for the larger system. So a test is a way to basically, it's like a safety net that you're always having around. And so as long as you're going to notice lots of ways your code could be better, where there's flaws or edge cases, and that'll happen throughout this whole cycle. But once you come back, you should make sure that you have that test at least logged. Does that answer your question?
Kind of, yeah.
Okay.
You know what I mean by exceptions to stuff you don't know, like it's catching it somewhere in your code. Are you saying there? Yeah, okay.
Yeah, I mean, there's always going to be bugs that we can't see, but hopefully in the cycle you'll kind of notice them as you go through.
Is the work on TDD at all related to kind of the research on confirmation bias and how learners tend to not look for the red fails, they look at what's working?
That's a great question. I haven't made that connection. I'm not sure what if there was a common origin in those two things, or if the people who are developing this use confirmation bias. I think it could be a useful way to, well, I'll get into that in a sec actually, because like the next step of TDD in a classroom setting is having learners write tests themselves and write in their own testing suite, or you can even have them swap testing suites, which is a really great way to kind of aggregate knowledge, is have people share their suites across their platform so that you're always like making sure you're not, thinking, just coding to whatever you expect the program to look like. Okay, so this is the big picture cycle. That's how it's generally described. And I've created a few examples for y'all to try. So I think the best way to do this is if you could go into groups of maybe 3 or 4. So maybe some of the big tables we can split off to some of the smaller ones. And one person who has a laptop and a good connection, pick one of these links to go to. And the first one is relatively easy. It's a series of tests for geometry. So it'll really just test, like, can you calculate the area of a square or a circle and that kind of thing. The next 2 are a little bit harder, and I created a JavaScript and a Python version in case any of you are more familiar with Python than JS and want to do that. These both two you can do in the browser. This one you have to download an actual script, so you have to have a Python environment set up already. And it's for calculating or converting an Arabic numeral to a Roman numeral. I'll open up this example to show you what I mean by what we're going to be doing next. So I've provided, this is the geometry one. I've provided some starter code and some starter tests. So this suite, for example, uses a rectangle object and tests the area function of a rectangle object, saying that you should be able to calculate the area of a rectangle and get the result. Same thing with circle. And then I've given some hints for future tests. So one for calculating the trapezoid area, and then an open-ended prompt for what other tests can you write, what other shapes do you want to calculate, or could you do something like perimeter, circumference, to write a test first, and then write the code to solve it. And there's also a little bit of starter code here. So the first test is already passing. I've written an example here. And then the beginning of the next one is ready to go. So you can pick this up, work as a team to solve those tests, and then start writing the additional tests to make it pass. OK, how did that go? Did anybody get did you get to the point of actually writing tests? You didn't solve them, but you got to write some tests though, right? OK, that's awesome. OK, so you got to red, yeah. You get to get the green next. All right, so I've got a few ideas about why I think this is useful and how I think it can be applied in an educational setting, but I'm curious to hear your thoughts now that you've seen it in action. Obviously, it's kind of a contrived example. This might not be something you'd use in the classroom, but it does have some of the principles here. Yeah?
I actually like it because in my ninth grade class, I like to have them think a lot about abstraction. You know, we can apply the same program to do various things.
Yeah.
So the nice thing about these tests is you can start off really specific. You could start off, testing for, I guess, pluralizing something, but then you can create more tests to see how far you can abstract your program.
Yeah, you can have tests that kind of grow with the program.
Yeah, see how many applications you can get.
Yeah, that's awesome.
Like a lot of people were using a ton of blended learning tools for our CS programs just because otherwise it would be unmanageable. And the tester becomes a real sort of daunting point for our program.
Yeah.
Where on CodeHS, they want the output in a particular way. I don't really know how they're testing it, so I can't tell them if they have a holistic answer, but they're missing a little test because there's a larger problem. So that's one of the deficits of doing it that way. Writing our own testers, first of all, would help them understand how their code is being checked out. A lot of them don't even know that that's what's happening, is that the system is sort of putting in different entries and seeing if the response is right. So I like sort of taking that out of the dark. And ultimately, if they wanted to make something they care about, they have to build their own tester. So if you want to truly get away from just textbook learning, they're going to have to write nice specs, share out their group, do testing that way. So I think this encourages, it encourages me as a teacher to kind of get away from just doing whatever the system wants, the project system is going to check.
Okay, excellent. Right here.
I was just thinking it teaches them about reason, what is reasonable, right? Instead of just having some crazy thing and they go crazy. So from before, they're predicting what's reasonable within the range of, reasonable outputs.
Yeah, having the output in mind.
Yeah.
I teach younger children and I teach Scratch. And I teach a lot of different ways based on kids and the size of the group. So when the group is large, I'm still in an independent school. The programs, the curriculum is more regimented. And I've essentially, even though there's no tester in that environment, I've essentially created the test like a checklist. Your maze game has to have these elements in it. So I have done the thinking of the testing because I need to in order to make sure that everybody in the class takes a certain level of skill. If I'm teaching a smaller class after school, I let them spin off in many different directions and it's more creative. However, what happens even in that smaller environment is they get so creative that they're not thinking, what if the person next to me has to play what I'm making? Mm-hmm. So if it's time, you say, okay, kind of go backward and say, well, let's take 2 weeks at the end of this after school session where you're going to have to, you came up with your testing. It's not as mechanized as this, right? But what you're going to challenge the person next to you, where you're going to ask them to look for. And so I think it'll kind of, within their own system of concerns, rein them in a little bit to create something that actually works, but not with the checklist, with the tester that I made in the larger environment. Yeah. So that's just how I'm translating this into using it with the other kids. It's actually a really interesting thing to me.
That's great, because it actually mirrors very closely kind of the origins of this. I mean, this is called technically automated testing, because originally software testing was like they would give people a script, be like, type this entry into this program and it should print this out, and then like mark a checkbox that it works. So this used to be jobs for thousands of people. They just like go through and do this. It's really, really boring. But now they have the automated testing suites.
So, since CS isn't my first language, English and history teaching is, like, I really like this idea because I feel like I could use it for teaching US. Because I could say, okay, so what's the purpose of a government? The thing is, the test has been run. It is called history, right? And so it's a great way of getting kids to engage by thinking about how it's supposed to be versus like how it actually went and what sort of how the design of government hasn't necessarily worked or has worked the way it was supposed to.
Yeah.
So it's a good way of like kind of sneaking in this way of thinking.
Cool. Yeah, the Constitution is basically one giant testing suite that we've done a mediocre job of accomplishing in history. Yeah.
I've been teaching AP level computer science, and the difficulty I've found, like I would like to do more testing. The difficulty I find is that, especially with more complicated programs, that writing the test suite itself is much more time consuming than writing the program.
Yeah.
Like in any real programming. And like I don't have the time to write all of that. And asking the student to do it is unrealistic because they struggle so much with just learning the basic programming that if you ask them to write a suite, they'll spend like all the time doing that. Like that's the difficulty I have.
Yeah, that's a great point. That's one of the downfalls, and so I hope that at least like some of maybe the simpler ones, or just have 2 or 3 tests like that are only console log or something, can be just like a nurture. And I'll talk a little bit at the very end about some kind of baby steps you can make towards using testing suites and stuff. But let me go on. So those are all great ideas. Thank you for sharing those. I wanted to share just a couple of my ideas for how this is useful. So one of them I think is that having frequent and terse feedback loops is a really useful tool where instead of kind of solving a problem and then going to have to ask somebody else, like, is this correct? What do you think? Like, you can have this very close cycle of, okay, it's working, it's not working, it's working, it's not working, and a very clear explanation about why and where my errors might be. So having that, I mean, the same way that errors are in regular programming, it's useful to have those terse feedback loops. What I mentioned at the beginning of discerning between errors of design and errors of implementation, I think this is a really critical skill in any kind of CS platform, is being able to understand when my idea about a problem is correct, but my implementation is wrong, versus when my idea about a problem is incorrect. And so I've got this dissonance there. And discerning between syntax error and an error because your test is failing is a really important skill to understand. Another thing and this is kind of a maybe positive, maybe negative, is that the measure of success becomes the test, not the teacher. That by kind of giving them a test suite, they're not testing against your expectations, but they get maybe one that they've created themselves. And so they get to define what success looks like for their own project, and giving them the agency and the autonomy to decide what my software should look like. This might be obviously a more advanced technique for later students, but I think that introducing little bits of it can be really useful. And yeah, this final one about allowing room for creative solutions within boundaries, that by creating a clear API for this, that you leave lots of room for implementation. And so in a classroom of 30 students, you can give them the same test suite, and they can compare their different solutions and look for innovative new ways to solve the same problem, rather than all looking for the exact same solution, kind of line by line, copying whatever it was that their partner is doing. Because they all still agree, and there's many ways to succeed. And then some of the dangers. So you mentioned one, just like, yeah, it's a big upfront cost. There's a lot of overhead, especially if you're using a testing framework like Jasmine in JavaScript, or in Ruby there's one called RSpec, which is really similar. And so there is an upfront cost, and this is the same thing in software, that you're basically saying, I'm going to spend a lot more time at the beginning designing in the hope and expectation that it'll make my implementation a lot faster, and it'll reduce the likelihood of errors in the future. So it's it's generally used by engineers who are working on larger projects over longer scales of time, where you really need that kind of security in place. For like a day-long sprint or just like simple exercises, tests might be not really worth the time. So have to choose like the appropriateness of the scope. And then the other thing is that, yeah, you can code to the test. That like if you just have tests, then the prerogative for the student is we'll make the test pass. Then you can run into the obstacle of not emphasizing understanding in their code, and just like making sure that they get it to pass, but understanding what they're actually doing. And the final thing is that there's such a thing as bad tests, that you can write bad specs. That's not uncommon. You can write tests that are incomplete, that either like they test the wrong thing, and so you can throw people for a loop for a while. There was one in my test that I had to correct this morning. I was like, oh, I flipped the V and the I in the Roman numerals thing, and that would have been like caused you to go down a whole different road. So a testing suite has to be really good if it's going to work, especially for lots of people to use it at the same time. And then finally, I just wanted to mention, if you're interested in this concept, if you like the idea of testing and like the possibilities it has in the classroom, I would encourage you to explore sort of a higher level of testing. Testing is usually meant to refer to testing individual objects or functions in your code, very sort of low-level implementation details. And there's this further theory called behavior-driven development, which arises from not sort of saying what exact functions or little pieces of your code should do, but what actual user flows should do. So for example, it's a way to automate testing things like, when I click on this button on my screen, it should make a modal pop up. It doesn't specify what function what name my function should be or what objects I need to define. It's just a behavioral outcome. So it allows for a lot more freedom and flexibility to implement. And there are a few ways to automate this that are pretty interesting, especially in the context of the web, of like working flows through different applications. And we have 3 minutes left, so I know I'm like cutting right down to time here. But I just wanted to wrap things up and ask if there's any further questions about testing that I can answer here, or critiques. I'm open to those as well right now that I can answer before we wrap up.
Are there any nice simulation programs that you could look at for testing that simulates the process?
Oh, yeah, great question. So I know mostly about web testing, and there's one called Selenium, which you should take a look at. It's got a bunch of different drivers, but basically it's an automated, it mimics somebody navigating a web page, and you can have it play out the videos. You can say, like, click on this button, then go to like this link, and it'll actually show you. You can like see the video of them typing out the thing. Selenium, yeah, SELENIUM. And I think for other platforms, there's other ways to like kind of
Like just a model for the kids if you don't want to go into the whole thing.
Exactly.
Just to get the feel of it.
Yeah. All right.
Oh, can you put your Prezi link on?
Oh, sure.
Down here, like.
Yeah, I'll put it in my under my section here, my links.
Yeah, down here, exactly.
Yeah, I'll be around for lunch if you have more questions about this. I'd be happy to talk about it more. But thank you all for coming. It was really fun to get to talk about this with you.